Okay, so we were lecturing on number theory, right? So in today's lecture, we are going to continue from where we left our last lecture. The topic that we are going to start our lecture today with is equivalence relation. Now, we know what a relation is in terms of mathematics, right? For example, most of us are familiar with equations look that look like this. Y equals to sum f of x. Basically, most of the time we deal with functions. We rarely deal with relations that are not functions, but those who are not functions are also relations. So technically, relation is something that is, as long as we are dealing with two variables, one input and one output, a relation is any relation between the two variables x and y, right? So this form is actually an explicit form. Sometimes we have this form as well, g of x y is 0. But yes, sometimes we describe the relation between x and y with words instead of mathematical equations. And uh, for example, one example of a relation can be y equals x squared, or just f of x equals x squared. Now, for today's lecture, there are different ways a function can be described, right? You can describe the function directly writing an equation between x and y, or you can write in this way, or you can write like this, x comma x square, right? Because technically, a relation between x and y is at the end of the day a graph in 2D. So y equals to x squared looks like this. So instead of describing the equation like this one or this one, you can just note down all the set of all the points that are on the curve, and it would still describe the same curve. So you can write the relation like this, x comma x squared, such that x belongs to the set of real numbers. So uh, under the example, all three are basically same. They describe the same thing. And sometimes we just write R equals. This R stands for set of real numbers, and this set of real numbers is not written like this, rather written like something like this. In textbooks, we write bold R's for real number, but we cannot write bold when we are writing on with pen and paper. So we take the advantage that we can just use a double line here. And this R is a single R, no double lines involved. So a relation we can write a relation in this manner as well. And for today's lecture, we are going to follow the last one, the last method. So, so this is what a relation is. Now, what is an equivalence relation? Basically, there is a definition that involves three conditions. A relation R is called an equivalence relation if following conditions hold. Number one, A comma A belongs to the relation. This is called symmetry, and you can understand why. Number two, A comma B belongs to R should imply B comma A also belongs to R, and this is called reflexivity. I think I mixed up. The first one is reflexivity. The second one is symmetry. And the reason behind the name should be self-explanatory. And number three is AB belongs to R and BC belongs to R should imply AC belongs to R. Now, the last one is called transitivity or the transitive property. If any relation follows these three conditions, then we call that relation an equivalence relation. Now, for now, this is just a definition. Someone who is not already familiar with the idea of an equivalence relation should not be able to see any direct motivation behind the definition, but gradually the motivations are going to be clear. Let's see an example first. Uh, the first example I'm going to show is pretty straightforward. Uh, let's use the function f of x equals to x. So technically, we are dealing with the points on the straight line y equals to x. And the domain is all real number. So we are taking x from the whole domain. Now, how can we write this in ordered pairs? Just the way we said we are going to use, we are going to write relation to them. So we can just write x comma x such that x belongs to the set of real numbers. Now let's check if it satisfies all the three conditions. First one. Now by default, a comma a belongs to R for all a in the set of real numbers. The two R's are different R's. I think let's do something to avoid the ambiguity. Let's name the relation F so that there is no ambiguity, right? So, and if this also makes sense because the name of the function was small f, right? Number two, if somehow you have a pair a comma b belongs to f, this would mean b equals to a, which would mean b comma a and a comma b are same thing, and a comma b belongs to f, so b comma a belongs to f. So symmetry is satisfied as well, just like reflexivity. Finally, transitivity, say you have a comma b belongs to f and b comma c belongs to f, then this would imply a is equals to b and this would imply b is equals to c. So technically we have a equals to b equals to c, right? So now we have to prove that a comma c also belongs to f. And what is a comma c? You can just replace c by b, right? Keep a unchanged, replace c by b because b and c are equal, and ab belongs to f. So we were able to prove the transitivity as well. Therefore, the relation f is indeed an equivalence relation. Now, I have mentioned a while ago that, a few minutes ago actually, that sometimes we describe a function or a relation with words instead of direct implicit or explicit expressions. How so? Let's see our next example. Define a relation. This is basically, let's take inspiration from the last example, actually. Uh, in the last example, we can define this relation by equality, right? And we can just rewrite this relation with words like this. Define equality by um, A equals to B whenever A and B are same real numbers. Now, we all know what an equality is. So this kind of sounds funny because as if someone is teaching us what an equality is. But say, for example, just for the sake of argument and understanding the main topic uh, or the more complex examples, let us first consider that we do not know what an equality is. Someone is just introducing equality to us. So equality of two real numbers are we are just defining it, that if two real numbers are exactly identical, then we call that A and B are equal. So this is how we are defining equality. We already have a symbol for equality, but we do not have a symbol for every relation on earth. You and I can mention 5, 10, hundreds of examples right now in the next 10 minutes. And we are not going to have a ready symbol for every relation, just like this equality sign. So that is why um, sometimes we have to use I mean, what can I say? Instant user made symbol for a new relation just we are describing. For example, this new example, define a relation, we are using the symbol that kind of looks like this. Define a relation this by A, this B, if and only if modulus of A equals to modulus of B, where A and B are real numbers. So if we had to, if we had to rewrite the same solution we did here using this equality notation, all we had to do is simply write A equals to A here and B equals to, and we had to write A equals to B implies B equals to A here. And in this case, we already wrote what we wanted to write. We had to write A equals to B and B equals to C implies A equals to C. So instead of writing these pairs belonging to this set F, we could just use the symbol equality and write the three lines in red color, right? That would be sufficient. Similarly, in this example on the right-hand side of the board now, we can just check the conditions one by one and just write this. Modulus of A and modulus of A are same anyway, which implies A is related to A anyway for all A in R. The second condition looks like this now. If A and B has same modulus, in fact, to be more formal, start with A related to B, which would imply modulus of A is equal to modulus of B, which would imply modulus of B equals to modulus of A, which would imply B is also related to A. And this is for all real numbers AB. Kind of looks silly because they are too simple, but we are going to introduce a more complex example pretty soon. And finally, if we are given that A is related to B and B is related to C, then it would mean modulus of A is equal to modulus of B and modulus of B equals to modulus of C, which would mean if you combine the two equations, you have modulus of A equals to modulus of C, which would finally mean A is related to C, and this is true for all A, B, C in the set of real numbers. So all three conditions are satisfied. So the relation we defined here using this weird symbol is actually an equivalence relation. Please let me know if you are uncomfortable with the new method or new symbol I just used to write a relation instead of just ordered pairs. If not, I think I can continue. Please let me know if you do not understand anywhere, any topic anywhere. So now let's introduce a more complex example. Not really. Let's show an example where the relation is actually not equivalence. So maybe what if I use the function? Let's see what happens finally if the three conditions are satisfied. F of x equals to minus x. So, which means we can write the function by x comma minus x such that x belongs to the set of real numbers. We are choosing the set of real numbers as domain, but I am more interested in writing it with the new symbol. You can use other symbols as well, but the symbol I wrote here in the last page, this red symbol, this is the most commonly used. So define a relation this by A is related to B if and only if B equals to minus A, where A and B belongs to the set of real numbers. Now, the first condition, A is not equal to minus A. So we are done here. No point progressing further, right? But just for the sake of fun, let's just continue the argument. What about the second one? If I want to be a bit more formal, I have to write A is not related to minus A. In the second case, so we are done here. In the second case, if we consider that A is related to B, it would mean B equals to minus A, which would mean A equals to minus B, which would mean A is related, B is related to A. So the second condition actually holds, but doesn't matter because the first one doesn't. Let's experiment with the third one. If we consider that A is related to B and B is related to C, this would mean B equals to minus A and C equals to minus B. So what about, if we just, therefore C, which is minus B, which should be equal to minus A, which is equal to A. So C is equals to A, which means C is not equals to minus A, which means A is not related to C. So only the second condition holds, but the other two don't. So in this example, we got that this is not an equivalent relation. So not equivalent relation. In the other examples were examples of equivalent relation, but this one is not. Well, now let's see an interesting property that comes out from the idea of equivalence relation. Not property actually, to be honest, and a new idea that comes out from the existing idea of equivalence relation. Say this is a set. We are using Venn diagram kind of thing. So this is a set of all the members in some set S, which is a domain, of course, on which we are going to define an equivalence relation. And say, for example, we choose a particular member A, a point A in the set, and somehow we develop a process to find all other members of S who are equivalent to A according to this relation. So say, for example, every member on the left of this red line are equivalent to A and hence equivalent to each other. How do we know they're equivalent to each other? Because if we have a member here and another member here, say this is A1 and this is A2. Now, A1 and A2 are both equivalent to A, and according to the transitivity, the transitive property, A1 and A2 should be equivalent to each other because they're equivalent to the same guy A. Now, let's choose any member from the right-hand side of the red line. For example, let's denote that guy by B. So say this is B. And do the same process again. Find all the members that are of S that are equivalent to B. And keep going like this. Find another member who are not part of any of the two sets I just drawn, and just choose a member which is on the right-hand side of the brown line. Say that member is C. And find all the members that are equivalent to C and partition them and keep going. My question is, okay, basically for simplicity, let's avoid drawing the dotted lines, and let's just consider that all the members are covered. So we got just three possible brackets or three possible partitions. Now, my question is, I have already used the word partition, but actually I did not prove with any argument that there is a partition. When we use the word partition on a set in mathematics, we mean that the subsets are actually disjoint. But is it the case here? To understand if it is or not, we have to make sure that, or we have to prove that none of the member here is equivalent to none of the member here. How can we understand? How can we prove that this is not true? For example, if somehow a member of the red subset is somehow equivalent to a member of the brown subset, then according to transitivity property, all the members in the brown red subset are going to be equivalent to the point B, or any point in the let me actually write names. Say this is X and this is Y. If we somehow manage to prove that X and Y are equivalent, it would mean that Y is equivalent to A as well, according to transitivity property. And using the same property, we can claim that Y is equivalent to every member in this first subset. Using the same logic, we can also prove that X is equivalent to B, according using transitivity, and hence X is equivalent to every member on the brown side. So these two subsets are going to be submerged into one another, right? They are going to be clashed into one another, and they would become the same subset. So it's never going to actually happen. They are going to be mutually disjoint every time, as long as you did your job properly of finding the equivalent members. So this argument means using any equivalence relation on any set we choose, on any set on Earth, if you manage to find an equivalence relation on the set, then using that equivalence relation, we can divide the set into partitions, which are mutually disjoint to each other. And this is going to happen for every equivalence relation. And inside every individual, we call these partitions classes. All right. So in each class, every member is equivalent to every member. And this is true for a member for himself also. That mean what I mean by that is A is equivalent to A itself also, which is ensured from the first condition of the that we used in the definition of equivalence relation, right? And also, if A is equivalent to B, another member A1, then A1 is equivalent to A also. This goes both ways, which is ensured by the second condition, and transitivity ensured the partitioning, the main idea, the governing idea of partitioning. So the conclusion is any equivalence relation on any set S divides the set S into mutually disjoint classes. These classes are called equivalence classes. Please let me know if there is any confusion on the topics we discussed so far. Otherwise, I'm moving on. Now let's come to the target example, the main example I've been waiting eagerly to introduce. Say we introduce an not we cannot claim this and a relation and the symbol we're going to use is this sign defined by we call this congruent. So this is, where do I write? Oh, okay, let's write later. A is congruent to B if and only if some number n, let's skip n for now. Let's choose a particular number 3. Some number 3 divides A minus B. This is the definition. We read this as A is congruent to B, but we do not stop here. We say modulo 3. Sometimes, in fact, most of the times, we write, what am I writing? I'm writing right, wrong. Sometimes we write A is congruent to B, and we write mod 3 in bracket, short for modulo 3. This part is important because we are defining the relation with respect to the number 3. The number 3 is important here. We could define a similar idea using in the number 5 or 4 or 10, right? So we are just mentioning what number we used. Now, let's see if this is an equivalence relation. First of all, A is equivalent to A modulo 3, since should be straightforward. 3 divides 0, which is A minus A. So any number divides 0 other than 0 itself. So this is true. If we have A is congruent to B modulo 3, this would mean 3 divides A minus B, which would mean if a number is divisible by 3, its negative is also going to be divisible by 3, right? So 3 divides negative of A minus B, which implies 3 divides B minus A, which implies B is congruent to A modulo 3. And finally, if it is given that A is congruent to B mod 3 and B is congruent to C mod 3, this would mean 3 divides A minus B and 3 divides B minus C. So if two numbers are divisible by 3, their summation is also divisible by 3, right? So 3 should divide A minus B plus B minus C, which implies 3 divides A minus C, which implies A is congruent to C modulo 3. So therefore, congruence modulo 3 is an equivalence relation. Please let me know if there is anything confusing. So now you should be able to see that if we just started with, if we just started with n, some number n instead of 3. In fact, if we just started with 5, the proof would be exactly same. All we had to do in that case is just replace 3 by 5 in our proof. In fact, we could use any number n where we didn't even specified n, and we could still make the proof work by replacing 3 by n. So, in fact, congruence in general, congruence modulo any number n is an equivalence relation. Now, let's explore this particular relation we just defined a bit further for the special case example of n equals to 3. When we say that 3 divides A minus B, this means A and B must have the same remainder when we divide them by 3. For example, if you have a number 5 and a number 3, their difference is not going to be divisible by 3. But if you have a number 5 and another number 2, their difference is divisible by 3. Because 5 is a number 2 plus a number divisible by 3. 5 is actually 3 plus 2, and 2 is actually 0 plus 2. So in fact, if you have a number 3k plus 2, another number 3l plus 2, their difference is going to be divisible by 3 because the 2's get cancelled by each other, right? And if you replace the similar expression, just replace 2 by 1, the value of k and l doesn't matter. It's going to work. And another case can be 3k minus 3l. Their difference is divisible by 3. But you cannot write any more cases because the number of possible remainders when you divide an integer by 3 is just 3 possible cases. No remainder, that is 0 remainder, 1 and 2. You cannot find any other integer as remainder when you divide an integer by 3, right? So we say that, so the idea is if you divide A and B and somehow find out that the remainder is same for both of the cases, then their difference is going to be divisible by 3, which would mean they are going to be congruent. So technically, two integers are congruent modulo 3 if they produce the same remainder when they are divided by 3. So we say so a number can be congruent to 3 possible cases: 0 mod 3, 1 mod 3, and 2 mod 3. And what are the numbers that are 0 mod 3? You know, 3 or minus 3, 6 or minus 6, and so on. What are the numbers that are 1 mod 3? You can write 4, you can write 7, you can write 10. You could subtract 3 from 1 also. So -2, -5, -8, and so on. All these numbers are congruent to 1 modulo 3. And similarly, 5, 8, all these numbers are congruent to 2 modulo 3. So technically, we have already divided the set of integers into 3 partitions or 3 equivalence classes, where the first class contains all the numbers that are congruent to 0. The second class contains all the numbers that are congruent to 1, and the third one contains all the numbers that are congruent to 2. So we have 3 somewhere here, 6 somewhere here, and so on, etc. So the entire set of integers are partitioned into 3 mutually disjoint classes. The same concept we discussed here, that any equivalence relation is going to divide a set into mutually disjoint classes. In this example, we got 3 classes. So in this string, if you take any 2 random numbers, for example, 6 and -2, and take the difference of them, that is 9, this result is going to be divisible by 3. Do the same for any number from this string as well. You can take just 8 and 5, and difference is 3, which is divisible by 3. This is how it works. Now, this works for every integer n, not just 3, of course. 3 is an example using which I established the concept, but it works for every integer. Okay. Now, if you have A is congruent to B mod n, you can basically, now we are going to build on this. Even though this is just one particular example of equivalence relation, just like the other ones I showed earlier, but I'm going to build further concepts on this particular example. This particular example is not just any example, this is special to us. So I'm going to build on this. So let us consider that we already have a congruence relation here. A and B are 2 integers which are congruent to each other modulo n. Then we can just multiply on both sides using the same integer. So we can just say Ka is congruent to Kb mod n. So technically, we are developing arithmetic. We are developing arithmetics, which means addition, multiplication, etc. Arithmetic. And what kind of arithmetic is this? It's called modular arithmetic. So how can we prove this idea? This is pretty simple. Proof. I'm not going to prove all the claims I'm going to show. Let's just show a couple of proofs to show that the proofs are not difficult. Say we already have A is congruent to B modulo n, which means n divides A minus B. This should mean n divides K times A minus B. In fact, n should divide any integer multiple of A minus B, which implies n divides Ka minus Kb. Now use the definition of modulo n, so that we can just write Ka is congruent to Kb modulo n. Similarly, we can just write, this is one rule. Another rule is A is congruent to B mod n implies A plus C is congruent to B plus C modulo n. And this should be visible to you because we are adding the same number to both of the numbers A and B. So the remainder when we divide by n remains same because we are adding the same number, right? The remainder remains unharmed. And we could subtract as well. Then comes the burning question. We subtract and added the same number, the equation remained intact. We multiplied with same number, the equation remained intact. What happens if we divide by same number? we have a problem while dividing. In some, if I show by example, in some examples there won't be any problem, but in some other examples there is going to be problem. Because, for example, 4 is congruent to uh, um, what example can I use? 6 is congruent to 16 mod 5. Why? Because 16 minus 6 is 10, which is divisible by 5. Some people like to think like this. Both are 1 mod 5. Some people like to think of mod as a remainder operator, even though it is not necessarily. But some people find it comfortable to think it like a remainder operator. So 6 and 16 both produce 1 when they are divided by, both produce a remainder of 1 when they are divided by 5. But the more accurate idea is 16 minus 6 is 10, which is divisible by 5. So this is a true relation. Now, if I divide both sides by 2, because I can, right? So 3 is congruent to 8 mod 5. What I get is still true. 8 minus 3 is 5. So the one above implies the one below. So this is okay. But let me show you another example where it is not going to be okay. For example, 5 is congruent to, okay, 25 is congruent to, what example? Let me find a suitable one. 24 is congruent to, uh, 16 modulo four. Okay, let's use 4. Let's use another number. Uh, 20. Let's use another example. Let me find a convenient one, the one that supports my claim. Okay, so 15 is congruent to 9 mod 6. Okay, this is a better example. So we uh, if we feel too comfortable observing the example above, we may end up writing something like this: just divide by 3 on both sides. So to produce 5 is 3 mod 6. But 15 minus 9 is 6, which is divisible by 6. But you should be able to see that 5 minus 3 is not divisible by 6. 5 minus 3 is 2, which is not divisible by 6. So this one does not work. This is a wrong example. So what happened? What is the difference between the two cases? The idea is, when I write 15 is congruent to 9 mod 6, what I mean is 6 divides 15 minus 9, which means 15 minus 9 is a multiple of 6, where k is an integer. Now, if you divide both sides by 3, you get 5 minus 3 is equal to 2k. So 2 divides 5 minus 3, and I should have written 5 is congruent to 3, which is true, but not mod 6, but mod 2. So something happened in between while I write the algebra in detail, right? But in the example above, this was not the case. If you write 16, if you write 5 divides 16 minus 6, and in a similar manner, if you just write 16 minus 6 is a multiple of 5, then if you divide both sides by what did I divide by? I divided by 2. So if you divide both sides by 2, I would get 8 minus 3. On the right hand side, 5 is not divisible by, this equation is correct because this relation is correct. 5 actually divides 16 minus 6. So there exists an integer multiple of 5 so that it is equal to 16 minus 6. But that integer multiple must be even because 5 is not divisible by 2. So k must be. So k takes the responsibility of being even, not 5. And in that case, 8 minus 3 is 5 times sum L. So finally, we can just write 5 divides 8 minus 3, which implies 8 is congruent to 3 mod 5. So in this example, 5 remains intact because 5 was not divisible by 2. But in this example, 6 does not remain intact because we could divide 6 by 2. So something happens differently in the two cases. And the idea is the number you are dividing with, what number I divided by in this case? I divided by 2 on both, I divided by 3 on both sides. And 3 actually divides 6. In fact, 3 doesn't necessarily have to divide 6. It shares a divisor with 6. So that is why 6, uh, this is the reason why 6 was reduced to 2 here. But in this
So,
case, when I did, yes, please.
so it should be like a prime number that we're dividing with.
Uh, Being prime is a sufficient condition, but it's not necessary. I can show examples where the number is not prime, the mod is not prime, but yet things happen. So prime is not the only issue. Being co-prime is the issue. That actually that is the logic I was going to develop anyway. Please keep listening. Keep continue to listen. Um, the number that I divided on both sides here is 3. And 3 shares common divisor with 6. And this is the reason. In this case, I divided both sides by 2. 5 does not share any common divisor with 2. If 5 had shared a common divisor with 2, even though if instead of 5, if I had 10 here, 10 shares a common divisor with 2, and things would happen differently, right? So the main idea is not being never divisible by anyone, but being sharing a divisor with the one that I'm dividing by. That is the main idea. So when let me use another color to write this one. A is congruent to B mod, let's write differently. AC is congruent to BD mod N would imply not BD. What am I writing? BC. Imply I can just divide by C on both sides if it is given that the one I'm dividing by, which is C, and the one after mod, which is N, do not share a common divisor, which means if C and N has GCD 1, just like the example in case of 5. So N does not have to be 5. It just have to be, N does not have to be prime. It just has to be prime to C. That would suffice. Is it clear to you who asked the question?
Yes, sir.
Okay, but what if we have actually, so let's write a a different variant of the rule number 3. What if we have this, and what if we have Cn equals to D, which is not 1 but greater than 1. In this case, what can I write? You see, in this example, not this one, in the example below, 15 is 9, congruent to 9 mod 6. When I divided by 3 on both sides to produce 5 and 3, I had to replace 6 by 2. So 6 had to be divided by 3 as well. I have to divide because there is this idea of cancellation on both sides here, right? So 15 was divided by 3, 9 was divided by 3, and so was 6. So in this case, I can write A is congruent to B, but inside I have to write not N, but N by D. But here is an interesting question that some of you might have asked. What if N by D is not an integer? N doesn't depend on A, B, or C, right? N is an independent number. So it was possible that the common divisor I'm dividing on both sides, which is C, and with C and N has, okay, I mean, this was actually, this is not a possible scenario because D is a common divisor of C and N. So D is indeed a divisor of N. So it was never going to happen anyway. So please never mind. So this is the variant of property number 3 when we are dividing on both sides by a same number. Just so in these cases, we have to be careful when dividing by the same number on both sides. We have to be careful if that number shares any common divisor with the N or not. Please let me know if everything is clear so far. If so, I'm going to move on. Now, why did I develop this modular arithmetic? This is going to be helpful in many ways. So let's see examples. There are other properties as well, but modular arithmetic actually belongs to the number theory branch called number theory, and we are not actually teaching a course dedicated to number theory only. This is a course that discusses different basic and fundamental topics from mathematics for freshers, right? So we are not going deep into number theory. Otherwise, there are other properties. For example, if A is congruent to, let's write another one. For A is congruent to B mod N, and C is congruent to D mod N, then we would have A plus minus C is congruent to B plus minus D mod N. Not only that, we would also be able to claim that AC is congruent to BD mod N. But of course, we cannot divide because division is complicated. And proofs are similar to this one, pretty simple. Just from the congruence relation, use the definition, do some algebra, and get back to the definition, use the definition again in the opposite direction. That's all. So you can, all of you can prove these ideas as well. There are some other ideas related to modular arithmetic also available in any standard textbook on number theory. Now let's solve an example. For example, we can solve this interesting problem using modular arithmetic. Find the last digit of 7 to the power 1, 2, 3. Generally, 7 to the power 1, you can understand 7 to the power 1, 2, 3. I think one of you have forgot to close your video. Turn off your video, please, all of you. Okay, I stopped it anyway. So 7 to the power 123, you are not going to calculate 7 to the power 123, of course, but we can use modular arithmetic. How? Let's see how. So basically, 7 square is 49, right? So, and 49 is when you say talk about last digit, you talk about any number mod 10, right? If you divide a number by 10 and take the remainder, it's going to be the last digit, right? If you have 1, 2, 3, 4, 12, 34, a number, divide this by 10, what is the remainder? The remainder is 4. So that is the last digit of 1234. So mod 10 plays a role here. So we can just say that 49 is actually 9 mod 10. But then again, 9 mod, what I'm going to do is actually raise power on both sides. So 7 square, we have 7 square, and we have some number mod 10 here. What I'm going to do is raise the power as high as possible so that I can get close to 7 to the power 123. But doing the, in fact, what number should I use in this box here? 123 is not divisible by 2. I have square here, right? 123 is not divisible by 2, but 122 is. And what is half of 122? Half of 100 is 50. And half of 22 is 11, so 61. So if you raise to the power 61, you would get what? 7 to the power 122, which is very close to 7 to the power 123. But that would mean raising the power of 9 to 61 as well. And that is still, that number is lesser in magnitude than 7 to the power 123, but still pretty huge. But we can do a trick here. You should be able to understand that 9 is also minus 1 modulo 10. Because 9 plus 1 is 10, right? Their difference is 10, which is divisible by 10. So we can just use minus 1 to the power 61. Now the question is this allowed? Is this valid? Raising to a same power on both sides of a congruence equation? The answer is yes, according to this one. I wrote this here, which means if you multiply two equation, that is going to be valid, modulo n. So multiply the same equation with itself to square on both sides. Then again to itself to cube on both sides. So we can understand that you can multiply a same relation with itself n times to raise the power to n. So which means what I did here is valid. This is interesting because this is congruent to just minus 1, I think. This is congruent to minus 1 mod 10. Now, are we interested in 700 and 122? Not really. We're interested in 700 and 123. And how to get that? From this, multiply by 7 on both sides. So on the next line, we can just multiply 7 on both sides to get 7 to the power 123 on the left-hand side and minus 7 on the right-hand side. And we have established that we can multiply by the same number on both sides. So when I divide 7 to the power 123 by 10, as a remainder, I do not really get minus 7 because remainder has a condition. It has to be, if we are making an attempt to divide B by A, then the remainder has this condition that it should be in between 0 and A, right? From 0 to the divisor. At best, it can include 0, but it cannot even include the divisor. So minus 7 doesn't satisfy this. It had to be within 0 to 10, but we can manage that. We can just add 10 with this to get 3 mod 10. And 3 satisfies the condition of a remainder. So 3 must be the last digit of 7 to the power 123. So the original task was pretty huge, but we just used a new kind of arithmetic we just developed to find the answer pretty easily. Please let me know if there is any confusion anywhere so far. If not, then I'm going to proceed with our next topic, linear congruence equation. What is a linear equation? In one variable, x equals to b. Now, we can solve this equation pretty easily, right? X is b by a. But now we are going to introduce a new kind of equation in modulo n, not 3n. So ax congruent to b modulo n. This kind of equation is called a congruence equation. And since there is no power of x other than 1 involved here, we call this equation a linear one. We have quadratic and cubic congruence equation and higher order congruence equation as well, but we are not going to discuss those in this course. We are going to limit our discussion to linear case. So equation of this form is called linear congruence equation. Let's see how we can solve such problems. For example, if you have let me choose a nice example. Let's try to solve 2x congruent to 1 modulo 15. Now, there are many ways to solve this. Two most common methods are what we are going to discuss. One of the methods involves Euclid's algorithm and linear Diophantine solution of linear Diophantine equation using Euclid's algorithm that we did in our last class. Let's see how. So solution 1. Since twice x is congruent to 1 mod 15, this would mean 15 divides twice x minus 1, which means twice x minus 1 is 15 times some y, which is an integer. So we have 2x minus 15y equals to 1. And this, in this case, x is already an integer for sure. And now we introduce the new variable y, which is also integer. So this is a linear Diophantine equation. And we can solve this linear Diophantine equation using the method discussed in our last class. We have discussed two different cases of linear Diophantine equations in our 2 classes before this one. And you know it involves finding the GCD of 2 and 15, then expressing that GCD in linear combination of 2 and 15, etc., etc. And finally, we can find general solution. We discussed method of finding the general solution in our last class. So pretty lengthy process, all right. And lengthy, but we know how to do that. And you can continue from here using that method. And at the end, you would get x and y both variable, but y is unimportant to us. What's important to us is the value of x. But I'm more interested in solution 2, which uses modular arithmetic. So twice x is 1 mod 15. What we can do, there are many ways. Basically, this depends. How we are going to approach from here on depends on you actually, and how sharp you are about finding paths to minimize calculation. The best method I can think of from here on is multiply both sides by 8. So 8 times 2x is congruent to 8 times 1 mod 15. I can do that, but what's the motivation behind multiplying by 8? Why 8? Let's see how. Why? Because we are dealing with mod 15. So we can take any number in this equation and replace that number by any other number which is congruent to that number. So we can just replace 16 by 1 because 16 is 1 mod 15. So 1 times x is congruent to 8 mod 15, which means x is 8 mod 15. So we have x with us. X is 8 mod 15. This is the answer. And you'll get the same answer using this method, but that method is going to be way longer than this one, way more lengthy than this one. But in this example, we could use other, in fact, we could think of other methods as well. For example, 2x 1 mod 15. Replace this one by 1 plus 15. We can do that, right? So 2x is congruent to 16 mod 15. We can divide both side by 2. And while dividing, remember, we have to, not 18. Why did I write 18? I added 15 with 1. So I should get 16 here. 16 and 1 are same number as long as we are mod 15, right? Now divide by 2 on both sides, of course. But be careful, because 2 and 15 do not share any common divisor. So their GCD is 1. So we do not have to replace 15 by anyone. But if it was something like 18, I had to replace 18 by 18 divided by 2, which is 9. So be careful when dividing on both sides. So this is the same answer. So we can use multiple methods, but there is a catch. Just like this step, where we divided by 2 on both sides, this could be the case that I had to, 15 is safe here because it does not share any common divisor with 2. But what if it did? Let's see an example of that sort. Let's see a simple example, to be honest, to describe the idea. Say, for example, our problem is tries x equals to, tries x is congruent to 12 modulo 6. Say this is the problem. So solution, we divide both sides by 3, x is congruent to 4, and 3 shares common divisor with 6, and the common divisor is 3 itself. So we have to divide by 3 to get 2. Now this is the solution, no doubt, but here is a problem. Let's write another line. X is congruent to 4 is 0 mod 2, right? Now, how many numbers are there modulo 2? 0 and 1, that's 2 numbers. So x can not exceed 1 as long as you are taking mod 2. But let's try to find out, we have modulo 6 here. So it's possible that from 2 to, between 2 and 6, there are other solutions, right? So of course, 3 into 0 is congruent to 12 mod 6, no doubt, because 12 is divisible by because 12 is divisible by 6. But can you think of another number here so that they became, that number, the product becomes congruent to 12 mod 6? What is 12 mod 6? 0. If you write 2 here, it also works. 6 is also 0 mod 6. In fact, if you write 4 here, this also works. If you write 6 here, this also works. But since we are dealing with mod 6, the answers can be in between 0 to 5. We are not going to accept the last one. This is a repetition, right? But we have 3 different solutions for this congruence equation, 0, 2, and 4. And we have got just one. This is because the interval 0 to 6, when we divided by 3 on both sides, 6 was divided by 3 as well to produce 2. So the overall length was made 1/3. And in fact, there are copies of this same partition here and also here. So we missed out the 2 copies of solution. We have a solution modulo 2 here, and we have missed another 2 copies of solution here. And how do we know there are just 3 solutions? Because we divided by 3. we partition the entire interval into 3 partitions. So there are other 2 copies as well. And since we are dealing with mod 2, the other solutions should be 0, 0 plus 2, 0 plus 4. You must know when to stop. You do not write 0 plus 6 because we already know we are going to get 3 solutions because we divided 6 by 3. If we divided by 7, we would get 7 solutions. So instead of stopping at the 3rd one, we had to stop at the 7th one in that example, if we had one like that. So final answer should be in mod 6. You cannot write mod 2 here. Then all these 3 would mean just 0 mod 2. So in cases of congruence equations where you divide, where the number you are dividing on both sides is not co-prime to the number inside mod, you have to be careful. After solving, you have to find if there are other solutions. When the GCD is 1, you have just 1 copy of solution, not 3 copies like this. In that case, this is the case where GCD is 1. So there is just 1 copy of solution. You can just stop here, or you can just stop here. But in case the GCD is not 1, you have to be careful about finding the missing solutions. So the main idea is, if you have an equation that looks like x equals to b mod n, if with GCD of, you are trying to divide by a on both sides, of course. So GCD of a and n, let's assume that's d. Then if x equals to x naught is 1 solution, then the solution set should be x naught is 1 solution. The other solution should be x naught plus, n by d, right? The second one should be x naught plus 2n by d. That is, keep adding n by d up to the point you reached x naught plus technically d minus 1 n by d. If you add another n by d with this guy, you'd end up getting x naught plus n, which is congruent to x naught, because we are in mod n. Do not write mod d by n here. Be careful. So this is the governing idea. That would be all. Please let me know if there is any confusion in the whole lecture, anywhere in the whole lecture. This is where we sign off from number theory, and we are going to start a new topic in our next class. I am not going any deeper into any number theory topics. Please let me know if there is any confusion anywhere in today's lecture. If not, I'm going to close the meeting. And all right, if there is no confusion, let's just end the meeting here. Good night, everyone.